So we finished off with the nomenclature of alcohols and started into certain reactions involving alcohols. Where our UPAC nomenclature finished up was with linear and cyclic alcohols, giving the UPAC rules for naming them. And we dove directly into reactions involving alcohols, specifically that reverse reaction that we looked at back in Unit 2, the dehydration of an alcohol to form an alkene plus water. Remember, if we turned that around, it was the hydration of an alkene to form an alcohol. But as I said in the previous lecture, most, if not all, organic reactions are in principle allowed to reverse, and that is what we covered last time. Very similar to that hydration of alkenes to form alcohols, specifically when we're working with now an unsymmetrical alcohol along with water being spit out to form alkenes. We have Zaitsev's rule, in which if we get two possible products, or alkene products, using Zaitsev's rule, many times we can predict the major product and the minor product of reaction based upon the substitution patterns on the resulting alkenes. So we will continue looking at reactions involving alcohols, and we're getting into now a very important type of reaction and a type of process in chemistry in general, and that is the concept of oxidation. You may have heard the term oxidation before. It's you see it in the media, you see it in many areas of life. Specifically with chemistry, oxidation can mean many things, and it can have many markers depending on what you're talking about. In general chemistry, oxidation can of elements, for instance, can mean something different than, say, if we're working with with compounds rather than elements. So oxidation is a very wide discipline, and we're going to be taking a narrow view on it, just how oxidation works in organic systems, And that's as far as we are going to take it. So an organic reaction, and here's a representative reaction right here in front of us, is considered an oxidation when the product loses a carbon-hydrogen bond and gains a carbon-oxygen bond. That is diagnostic for an oxidation having occurred. So importantly, we have to compare this starting material with the product and see if these two things happen. So if we look at the starting material here, we have, this is our carbonyl carbon, and we have in red a CH bond there, one of them. And we also have one carbon-oxygen bond leading from the carbonyl carbon, to the oxygen of that alcohol. Well, let's see what happens when we move over to our product over on the right. So again, we're looking at this particular carbon. There is now no CH bonds at that carbon. So we've lost a CH bond. So it's just not there because all four bonds have been used from carbon. Now, if we look at from that carbon, we have two covalent bonds touching oxygen. So now we have two CO bonds in the product, whereas in the starting material we had that one CO bond. So both of those criteria have been matched. So we do indeed this reaction here, going from this reactant to this product, would indeed be considered an oxidation. Now, speaking of reverse reactions, the reverse of an oxidation is known as a reduction in an organic system, a reduction. So they're a simple reversal of each other. In this reaction sequence you see on the bottom here, I've simply taken the product from the previous reaction and made it the reactant, and the reactant from the previous reaction and made it the product. And this sequence where we're going from this reactant to this product would now be known as a reduction. Why? Well, if we think of a reduction as the simple opposite of an oxidation in an organic system, whereas in an oxidation we lose a CH bond, in a reduction we gain a CH bond. And in an oxidation, whereas we gain a CO bond, in a reduction, we lose a carbon-oxygen bond. And we can see that in this bottom reaction right here, going from reactant to product. In our reactant, we have 2 carbon-oxygen bonds and no carbon-hydrogen bonds at that carbon. Well, in this case, in our product now, we have 1 carbon-oxygen bond and 1 carbon-hydrogen bond. So the amounts have gone down and gone up respectively to be diagnostic for a reduction. Now, we're going to spend a few slides hence talking about this idea of oxidation in organic systems. Reduction in organic systems we'll talk about at the end of the lecture. So to put this all together, we can track the oxidation level of a particular compound if you want, and relate it to the functional, many of the functional groups that we have already looked at. And if we had, for instance, an alkane and we converted that to an alcohol somehow, would that be an oxidation or a reduction? And similarly, if we had an alcohol and converted that to an aldehyde, same question, oxidation or reduction or something else. Aldehyde to a carboxylic acid. What is the structural change going on in each of these cases? And we would find that going from one to the other, going from left to right, that we're successively going to a more oxidized form, and we can see that now. So on this representative alkane here, we have 3 CH bonds, no CO bonds, and in this resulting alcohol, we lose a CH bond down to 2, and we gain a CO bond up to 1. Moving forward to an aldehyde, well, we went from 2 CH bonds in the alcohol to 1 CH bond in that aldehyde. Similarly, oxygen, carbon-oxygen bonds, we went from 1 to 2. Yes, that double bond, that carbonyl, that C double bond O, counts as 2 carbon-oxygen bonds. And lastly, going from an aldehyde to a carboxylic acid, we can say is indeed an oxidation. Why? Well, we lose the CH bond from the aldehyde, that carbon. Now there are no CH bonds. They're all CO bonds. And we go from the aldehyde going to the carboxylic acid from 2 carbon-oxygen bonds at that carbon to 3 carbon-oxygen bonds, which you should be able to see here. So we see this trend going from left to right as as we go to a successively more oxidized form. If we turn that arrow around and looked at those same 4 functional groups, we could say, well, we're successively going to a more reduced form, since a reduction is simply a reversal of an oxidation. It is the opposite of an oxidation. So we can now make some predictions, and let's take a look at the oxidation of alcohols. If you remember our classification of alcohols, we had primary alcohols, secondary alcohols, and tertiary alcohols as we worked out in earlier on. If we're presented with pretty much any alcohol, we can classify it based upon primary, secondary, or tertiary. And we're going to oxidize each of these, meaning we're going to react them with an oxidant. An oxidant, there are hundreds of oxidants out there. They are simply reagents which cause an oxidation to form. So an oxidant allows for or precipitates an oxidation to occur. And if an oxidation occurs, well, let's look up on the top at our primary alcohol. What are we going to build here if we lose a CH bond and gain a CO bond? Well, we can predict that. We'll take away that CH bond and add a carbon-oxygen bond. We'll make it a double bond, and that comes out to be an aldehyde. Indeed, always a primary alcohol will oxidize to an aldehyde. So keep those 2 in your mind. Primary alcohol oxidizes to an aldehyde always. Again, the structural change that we saw here we could predict, and that is the loss of a carbon-hydrogen bond and the gain of a carbon-oxygen bond. Let's look at the middle series right here, a secondary alcohol. That secondary alcohol, if we treat that with an oxidant, let's remember that the structural change associated with an oxidation is, as we saw above, a loss of a CH bond, gain of a CO bond. Let's see what that would produce if we did that. And I recognize that these products are sort of skewed off, written a little different than you might see them, but the connectivity is there, and I do that just so they match up a little bit with the starting materials. But that is indeed a ketone as a product. A secondary alcohol will always oxidize to a ketone. Always, it must, because of its basic structure. Once we lose a CH bond and we gain a CO bond, we must, by definition, get a ketone. So let's go back and look at these two alcohols for a moment. And what is a structural feature that essentially allows it to oxidize when that alcohol is placed in the vicinity of an oxidant? Notice these CH bonds in red here, CH bonds, because in order to oxidize, we have to lose at least one CH bond. So we have to have in our alcohol starting material a carbon-hydrogen bond at that carbonyl carbon in order for an oxidation to occur. And I tee this up because let's look down here at the bottom at our tertiary alcohol. Is there a carbon-hydrogen bond associated with that carbonyl carbon? No, there isn't. We have 3 R groups connected to that carbonyl carbon, and those are abbreviations for hydrocarbon type carbons themselves. There are other carbon atoms. So if our tertiary alcohol now is put in the presence of an oxidant, well, no reaction is going to occur. They're just going to sit there and giggle at each other. No reaction occurs because there is no carbon-hydrogen bond to lose at that carbonyl carbon. Therefore, no reaction. So in each of these cases, we have a predictor. Primary alcohols will always convert to aldehydes, or oxidize to aldehydes rather. Secondary alcohols will always oxidize to ketones. And tertiary alcohols, when placed in the presence of an oxidant, will not react at all. So I had mentioned before that there are hundreds of oxidants out there, possible oxidants, and we will be, for right now, referring to these as strong oxidants for reasons we'll see down the road. But of the hundreds of possible strong oxidants there are, we don't want to get too bogged down with all of these. I am going to be expressing 2 representative ones for the purpose of this course. So we have as our 2 representative oxidants potassium permanganate, or KMNO4, or chromic acid, or, you know, as it's its chemical formula, H2CrO4. So whenever you see KMNO4 or H2CrO4 as a reagent or over an arrow or something like that, that's going to tell you that there's an oxidation going on and I'm using a strong oxidant. All of these strong oxidants will produce those changes from alcohols to oxidations from alcohols to carbonyl compounds that we talked about before, as long as we remember those 2 reagents. So let's take a look at, we'll play some what's in the box here, and if we have this alcohol over on the left-hand side, and here I have KMNO4 is being treated with. KMNO4, well, remember that is one of our representative strong oxidants. So we know that the area of action, as it were, is right here. Nowhere else on this molecule is any action going to be occurring by this oxidant. It's only going to be dealing with that carbon-oxygen bond. So we see one carbon-oxygen bond there in that alcohol. It must go to a carbonyl compound. What I would do is just draw out the basic single-bonded carbon architecture in the box and throw in a carbonyl. So we've gained a carbon-oxygen bond, certainly. Now, importantly, we've also lost a CH bond, but I didn't show it here. Remember, there is a hydrogen there. This is line drawing, so this hydrogen is just assumed in this reactant, but over on the product, that carbon-hydrogen bond is gone, because as we can see at that carbon on the product, there is already 4 bonds emanating from it, so there can't be another hydrogen connected to it. So again, sometimes what's in the box is a little skewed. Here we have one where the box is the starting material, and we're treating whatever it is with H2CrO4, and we get this carbonyl product right here. So if we look at here is here is our carbonyl, C double bond O. That is the result of an oxidation, and indeed that is an oxidant. So the action on this particular molecule is at that carbonyl. So what we can do is draw that 5-carbon cycle, that pentagon, and instead of a carbonyl at one of those carbons, it's simply an alcohol. So once we get used to doing a few of these, we find out where the action is on those molecules, and then we would move forward and just either, whether we're talking about in the box as a reactant or product, just make the appropriate structure in the box. Now we can run into a potential problem when only using strong oxidants. And if we look at this reaction here, we have a primary alcohol along with one of our representative strong oxidants, KMNO4, and that is oxidizing to an aldehyde. We saw that. A primary alcohol oxidizes to an aldehyde. That's always the case. However, when oxidizing that primary alcohol with a strong oxidant, it does indeed go to the aldehyde, but it won't stop there. It continues on using remaining oxidant in there to the carboxylic acid. That is a more oxidized variant than is the aldehyde. Our aldehyde here has 2 carbon-oxygen bonds and 1 CH bond, which isn't shown here, but indeed there it is. We draw it in. And the carboxylic acid has 1, 2, 3 carbon-oxygen bonds, up from 2, so that is diagnostic for an oxidation. And right at that carbonyl carbon, now we don't have that CH bond anymore. So suffice to say, we have indeed oxidized that more. So starting with a primary alcohol, if I treat this with a strong oxidant, certainly it is going to move, is going to be oxidized to the aldehyde, but it can't put on the brakes there. It keeps on going until we get to the carboxylic acid. So really, treating a primary alcohol with a strong oxidant, we get a carboxylic acid because we have no way of stopping it at the aldehyde stage. It oxidizes until it can oxidize no more using that strong oxidant, potassium permanganate. Well, this problem has been addressed, and in order to solve it, there are different strengths, if you will, of oxidants, and we can actually recruit what is known as a mild oxidant. There are several oxidants known as mild oxidants, which will stop that oxidation of a primary alcohol at the aldehyde stage. And that'll put on the brakes. It does not go any further to form the carboxylic acid. It stops at the aldehyde. That's very helpful as an organic chemist if we're trying to design reactions. And we say, well, what if I want an aldehyde? I don't want a carboxylic acid. I want this oxidation to stop at an aldehyde. Well, we can indeed recruit a mild oxidant. And there are many possible mild oxidants as well. And I'm going to be, for the purpose of this class, showing you just one of them. One representative mild oxidant, and that would be known as pyridinium chlorochromate, kind of a mouthful. And when we get a word salad for many of these, we rely on the acronym, or PCC. So typically, if you see PCC as as a reagent, well, that's going to be a mild oxidant, and be working with it in that manner. So this primary alcohol, if we treated it with the mild oxidant PCC, it would indeed stop at our aldehyde stage, and that would be it. So we've solved the problem. If we needed an aldehyde from that primary alcohol and not a carboxylic acid, well, let's tune up our oxidant and we'll recruit a mild oxidant, in this case PCC. This also allows us for a diversity of synthetic potential, if you will. So let's take a look at what we could do with this just based upon our the usage of what type of oxidant. So here now we have an alcohol. It is indeed a primary alcohol, and we're going to treat that with PCC. We would remember that PCC is our mild oxidant, so that where is the action on this molecule? Only right there, that carbon-oxygen bond. Everything else stays the same. So treating with PCC, we'll take that primary alcohol to a representative aldehyde. Now, again, let me just, I say this a lot, but let me just say, look at this aldehyde. That is a carbon atom right there, ends in the bens, remember? And there is that hydrogen, that CH bond on that aldehyde. We just don't show it when we're working with line drawing. But to see the aldehyde as something like this can be disconcerting. Just remember we're in line drawing. Fair enough. We're able to take that particular primary alcohol to the aldehyde stage and leave it there. But what if we wanted a carboxylic acid? Well, I could take that primary alcohol and treat it instead with a strong oxidant. And in this case, we would, at that carbon, we wouldn't get an aldehyde, we would get a carboxylic acid. So let's dig a little deeper into the nature of what an oxidant actually is. Remember when I told you that a reduction was simply a reversal of an oxidation? Well, it turns out that in an oxidation reaction, there must always be ongoing a concurrent reduction at the same time. If that doesn't happen, an oxidation will never occur. So for one thing oxidizing, something else must be reducing. That must happen. So if I have, in this case, an aldehyde plus an oxidant, that is going to go to a carboxylic acid, because a carboxylic acid is a more oxidized functional group than the aldehyde. It has gained a CO bond and it has lost a CH bond. So we're going to call that an oxidation. But let's look back up top. With every oxidation, there must be a concurrent reduction. So if the aldehyde going to the carboxylic acid is the oxidation, what is the concurrent reduction? Well, this is where an oxidant comes in. We find that an oxidant is nothing more than a substance that can very easily be in itself reduced. So the product profile of what's left over from our oxidant is simply a reduced oxidant. I say that in a very hand-waving way without any structures, because many of these oxidants and the mechanisms of oxidation are quite complex, so we're not going to study those. But the actual concurrent reduction now is that oxidant becoming the reduced oxidant, and thus we can have our desired reaction, which we see here, this oxidation, by employing a substance which in itself is readily reduced. So we don't really follow the fate of an oxidant. We just use it for its practical utility, the fact that it likes to reduce. In fact, its impetus to reduce is so great that it actually pushes the oxidation along that we're actually concerned with. This aldehyde to this carboxylic acid is the purpose of this reaction. This oxidant traveling to a reduced oxidant is merely ancillary. It doesn't matter to the reaction. We are using it as a just out of practicality. So now we had looked back before at, I know that an aldehyde can oxidize. Why? Because it has this carbon-hydrogen bond at that carbon to pay sort of a price or a cover charge, if you will, in order to be oxidized. An alcohol that doesn't have a CH bond at that carbonyl carbon, remember, will not oxidize. We get no reaction. So let's keep that in mind as we try to use the idea of an oxidation towards a practical end. So, as before, we know that an aldehyde, when put in the presence of an oxidant, will oxidize because of the existence of that CH bond on that aldehyde. And indeed, we get exactly what we saw on the previous slide. The aldehyde oxidizes to a carboxylic acid, and the oxidant reduces to a reduced oxidant, whatever that is. But remember now, what if I bring in or recruit a ketone? What if I put a ketone in the presence of an oxidant? Will that oxidize? It actually will not, because at this carbon right there, is there a CH bond that allows it to be gobbled up so that an oxidation can happen? There is not one. There is no CH bond, so no reaction. Now, imagine if you had an unknown compound. You had a vessel of an unknown compound, and it was either an aldehyde or a ketone. Now, you were told that. It was either an aldehyde or a ketone. Could we leverage the fact that an aldehyde can further oxidize to a carboxylic acid, whereas a ketone cannot have a reaction with an oxidant? Can we leverage that and put it to our use in discovering if my unknown compound is a ketone or an aldehyde? Well, normally, no, you can't do that. And that is because most organic reactions are colorless. You cannot tell whether a reaction is progressing by sight. Usually. Sometimes you can, but usually it's invisible. I'm looking at a beaker with a solvent in it. I cannot tell whether this reaction is ongoing or not. I can't tell whether an oxidation might be occurring or not, because typically the aldehyde going to the carboxylic acid here, both of those are colorless and they're invisible, as well as the oxidant going to our reduced oxidant, that is similarly invisible. You cannot tell. However, what if we designed an oxidant which would give a visual cue for when it went from oxidant to reduced oxidant? We would see a visual cue. That would tell us whether an oxidation is happening. This would be invisible. But that oxidation would not occur unless our oxidant was being converted to reduced oxidant. So they go at the same time. Therefore, if we got a visual cue that this oxidant is going to reduced oxidant, we'd know that we had an aldehyde and not a ketone. Why? Because it's the aldehyde that oxidizes to a carboxylic acid, and our oxidant will not reduce to a reduced oxidant unless that happens. Let's look at a ketone. Here's our ketone over on the bottom, and if I treat that with an oxidant here, which will give a visual cue if it oxidizes, or rather reduces, well, that visual cue won't happen in the case of a ketone being mixed around with our oxidant, because no reaction occurs. So there are two types of oxidants that I'm going to be showing you that can act as tests to determine whether an aldehyde is present. If we're just looking at this narrow focus where I have an unknown compound and I need to know whether this is an aldehyde or a ketone. Somebody told me it was either an aldehyde or a ketone. Which one is it? Well, let's see which one oxidizes. An aldehyde would oxidize. A ketone would not oxidize. All right, so let's take a look at these tests. The first one is known as the Tollens silver mirror test. And in this case, we have a representative aldehyde. We'll show you which one actually reacts here. And our oxidant is a silver ammonia complex dissolved in water. It is colorless, as you can see right there. Normally, that is dissolved and it is colorless. So if we take this Tollens reagent, as it's called, and treat it with an aldehyde, well, that aldehyde is indeed going to oxidize to the carboxylic acid. That is invisible. We can't tell what's going on. But the Tollens reagent, being the oxidant, going from this colorless dissolved solution, when it reduces, what we get, the important thing that we get is, I've written this here as Ag0. That is metallic silver. Metallic silver. And that metallic silver plates out on the inside of the test tube. It's actually a very beautiful reaction. The inside of the test tube turns into a mirror. It's pretty amazing. And that would be considered a Tollens, positive Tollens test. A positive Tollens test, which would mean it was an aldehyde that was present. Whereas if we treated a ketone with our silver oxidant, we would get no reaction, meaning we would not get the solid silver plating out on the inside of the test tube. So that would tell us, okay, well, we didn't have a positive reaction, so that must be a ketone then, and not an aldehyde. That's what we're looking at here. To give you a visual indication of this beautiful reaction, we've got a series of series right here, in which we have, starting over on the left, we have our beaker, if you will, which has our Tollens reagent in it and an aldehyde. So we're showing you a positive test. And as the reaction progresses with that aldehyde, the mirror starts to form on the inside of that vessel. And then by the end of the reaction, we can see that that silver has plated out on the inside of that entire reaction vessel. Again, a very beautiful reaction. The next test we're going to look at, which offers a visual cue of that oxidant converting to a reduced oxidant, is known as the Benedict test. And for that, we use what is known as the Benedict's reagent as the oxidant. And that is this copper hydroxide reagent. It is dissolved into water. It forms a light blue solution, normally looking something like this. And if we treated this Benedict's reagent with an aldehyde, which we know is going to react, is going to oxidize, we get that oxidation, which again is not the important part because it's invisible, but we get this reduction for going to a particular copper oxide. And what's important about this is that copper oxide is a brick red precipitate. So this would be a positive Benedict's test. And you can see that's very specific, going from that see-through light blue solution to that opaque, non-see-through brick red precipitate. That is a positive Benedict's test. And that would be positive if we had an aldehyde present. Whereas if we take our Benedict's reagent and treat it with a ketone, we know that's not going to react, that oxidation won't occur, and thus that visual cue of forming that reduced oxidant will not occur, and we get no reaction. So that is the second in our series of two oxidants, which offer a visual cue that can tell us whether our unknown substance is oxidizing or not. Is it an aldehyde or a ketone? So we've talked a lot about oxidation of alcohols to carbonyl compounds. But what have we said a couple of times previously? That any organic reaction, given the right set of conditions and reagents, it can probably be turned around and reversed. Any organic reaction is in principle reversible. So when we have been talking about oxidation of alcohols to their corresponding carbonyl compounds, what's the reverse of that? Well, it would be the reduction of the corresponding carbonyl compounds back to alcohols. And so the heading here says reduction of a carbonyl compound to an alcohol. That's the reverse of an oxidation, what we were looking at before. But in order to introduce this, how we're going to be carrying out this reduction, I want to go back to a reaction we looked at back in Unit 2, the hydrogenation of an alkene to form an alkane. Using excess hydrogen under pressure and metal catalyst, either palladium, platinum, or nickel. The important thing I want you to look at here, if we look over on the left-hand side, is that alkene, that carbon-carbon double bond, goes to a carbon-carbon single bond. And a hydrogen adds on either side to one carbon and to the other carbon. So fair enough. So what if I took this part of the molecule off and instead put on an oxygen? We'd have a C double bond O, an aldehyde or a ketone. That's still a double bonded species. And it turns out that when I treat that double bonded species, that carbonyl, with hydrogen, excess hydrogen under pressure, in the presence of a metal catalyst, one of these three metal catalysts, I carry out the same type of reaction. That H2 hydrogen adds over that double bond, C double bond O, to C single bond O. Let's look carefully at what we have built now. We have a hydrogen on either side. What is that? Well, that is an oxygen. We have an oxygen atom here, flanked on one side by hydrogen and on the other side by hydrocarbon type carbon. That is diagnostic alcohol functional group structure. So how we carry out this reduction from an aldehyde or ketone into its corresponding alcohol is through the tried and true methods of hydrogenation that we've looked at before. So we can utilize this for turning around that oxidation into a reduction. So what we see here should seem somewhat familiar. It was a sort of a layout that we saw earlier in this lecture, and that is because we're talking about a simple reversal reaction here. We looked at this type of setup when we were talking about oxidations of alcohols to their corresponding carbonyl compounds. Now we're looking at the reverse of that. Carbonyl compounds being reduced to their corresponding alcohols. And if we look at the starting material on the top, that is a representative aldehyde, a general aldehyde, written suggestively to be able to recruit and bring in this diatomic hydrogen under pressure using one of these three metal catalysts, and we end up with hydrogen adding over that carbon-oxygen double bond to form a carbon-oxygen single bond. That would be a primary alcohol in this case. If you classified this alcohol, it would be primary. And what we see here, importantly, is that just as when we oxidized a primary alcohol, it always oxidized to an aldehyde. However, when we reduce an aldehyde, it always goes back to that same one, our primary alcohol. So it is a two-way street. In this reduction, we're actually seeing that diagnostic structural change of a reduction, the gain of a CH bond going from reactant to product, and the loss of a CO bond going from reactant to product. So one thing to just keep in the back of our minds, the hydrogenation of an aldehyde always yields a primary alcohol, just like I just said. The next one, we have a ketone starting material, again, written suggestively, treated with diatomic hydrogen in the presence of one of these three metal catalysts. And as before with the aldehyde, the ketones, carbonyl, C double bond O, hydrogen will add over that to give the corresponding alcohol. That is a secondary alcohol. So we get, on this reduction, the ketone always forms a secondary alcohol. Just like in the oxidation of a secondary alcohol, it always formed a ketone. Those two functional groups are always put together. And we know this is a reduction again because of this structural change, the gain of a CH bond and loss of a CO bond. So again, to summarize, the hydrogenation of a ketone now in this case always yields a secondary alcohol. A couple of your favorite game in mine, what's in the box? Let's take a look on this reduction of carbonyl compounds to an alcohol. Obviously, you wouldn't be told this is going to be a reduction, these two reactions, but we can sleuth it out. Here we have a carbonyl compound up on top, treated with hydrogen under pressure using this one of our metal catalysts, namely nickel. So what's going to go on here? We would see that, oh, this is a reduction of a carbonyl compound. So, here is where the action is on the molecule, nowhere else. So we find that what we would put in the box here is that reduction. We would go from a carbon-oxygen double bond to a carbon-oxygen single bond. It's as simple as that. Once we realize that this is a reduction, it's all over. We can just bring in, just put in an alcohol functional group where that carbonyl group was before. Our last one here, it gives our product, but it asks us in the box to say, well, what is our reactant? So we know that that is a primary alcohol that is formed over on the right. What is the precursor of a primary alcohol when we are hydrogenating or reducing it? Well, it must be an aldehyde. So I'm going to draw out this entire single bonded carbon skeleton, and where is my action point? That's it right there. Everything else stays the same, and that carbon-oxygen single bond will go to a species which has a carbon-oxygen double bond. Now notice in this case, in this aldehyde, I have elected to draw in that carbon-hydrogen bond that every aldehyde has. Sometimes I don't do that, which makes some aldehydes look a little different than others. So it is important to pay somewhat attention to this. However, if you drew it without that carbon-hydrogen bond, that would be fine too. Just knowing that it must be an aldehyde that reduces to a primary alcohol.